Okay, so in your note, once you grab your notes, here's where we left off last. Remember when that was? Probably Monday, right? We were we were talking about the first derivative test, and we were looking at an example to kind of illustrate how this works. Here's our example. We want to find all the open intervals on which the function is increasing and decreasing and find all relative extrema for this function, right? And we took first derivative, and we found the first derivative, here it is, and we're in the process of getting our critical numbers, right? So we know that critical numbers occur at what two kinds of places where the derivative does what or what? Zero or undefined. Okay, so where would it equal zero? One of the real benefits of writing our derivative as a rational function is we know that the rational function is zero when the numerator is zero, right? And we found those places to be the numerator is zero when x squared minus 4 is zero, which is when x equals plus or minus, when x to the fourth minus 4 is zero. And we were just in the process of talking about how to find those roots. And this is kind of a little pre-algebra review stuff, right? So how do we solve the equation x squared minus 4 equals 0? So one way we can do it is we could isolate x. We could say x to the fourth equal to 4. But then the part that I want to caution you to be careful with there is if you use this route, you're going to miss some complex solutions that have imaginary parts, right? Which for now isn't a big deal, but eventually it will be, right? So I could take the plus or minus the fourth root of that, and the fourth root of 4 is just going to be square root of 2, right? Or even better, if we were to set this equal to, if you have you're trying to take an even root of both sides, you can still use the strategy of isolating x if if you do successive square roots, right? Because if I square root both sides, I'm going to get x squared equals plus or minus the square root of 4, which is 2, right? And then when I take these two equations and I solve those, look what happens. X squared equals 2 when x equals what? Oh, it's bad color. When x equals what? Plus or minus square root of 2, right? But look what happens over here. X squared equals negative 2 when x equals what? Plus or minus the square root of negative 2, which is plus or minus radical 2i. Now, I wouldn't have gotten those if I just took the fourth root of both sides, right? Does that make sense? So it's better if you do successive square roots, okay? I don't need those for now, though, because we're only looking for real solutions. It's probably better to factor. If I think of x to the fourth minus 4 as a difference of squares, I could factor that into x squared minus 2 times x squared plus 2. And then that's going to quickly give me my solutions. X equals plus or minus radical 2. And then these I would recognize are giving me complex solutions with imaginary parts, so I can just discard those. Okay, make sense? Okay. All right, so we got our critical numbers. For the critical numbers for when the derivative is equal to 0. Okay, so now what about the other kind of critical numbers? What about the critical numbers where the first derivative is undefined? Where is a rational function undefined? Where the denominator is 0, right? So we can see right away, we don't even have to really do anything fancy here. We just know that f prime equals is undefined. At x equals what? 0. So we got 3 critical numbers to check, right? Okay. Let's go to another page and let's just transfer everything that we've done to the other page, and now we're going to use the table to apply the first derivative test. Okay, and we'll remind ourselves what that even is. So here's what we started off with. We found that our derivative, let's see here. Nope, that's not it. That's what we're doing. So there's our function, we found that the derivative, do you guys remember what the derivative was? Wasn't it, what did we end up getting? 2 times x to the fourth minus 4 over x cubed. So, and x to the fourth minus 4, I'm going to call x squared plus 2 times x squared minus 2 over x cubed. There was our derivative function, okay? Which gave us critical numbers. We got f prime equaling 0 at x equals plus or minus radical 2. And we got f prime undefined at x equals 0. Okay? So first derivative test. Let's go back and remind ourselves what that is. We hadn't really talked about this. We just mentioned the words. The first derivative test is telling us that we can determine whether a critical number is a minimum or a maximum, a relative minimum or relative maximum, just by looking at the signs of the slopes on either side of the critical number. You all told me that it makes sense that an increasing function is a place where the derivative is greater than 0, it's positive. That means the ant is walking uphill from left to right. A function is decreasing if the derivative is less than 0, okay? And we have a horizontal tangent line if the derivative is equal to 0, right? Okay? So what would happen if we made a table then with these critical numbers? And one other thing we want to make sure we're always including is what's the domain of our function? What's the domain of our function here? Except 0, right? It's all reals, and how come we can't have 0? Because it's undefined, right? So we know our domain is x cannot equal 0. And so really, you know, we should consider that from the very beginning, because what does that tell us about our critical numbers? Is 0 a critical number? No, it's not, because if the function's undefined there, we already know the derivative can't exist if the function doesn't exist, right? You get that? The derivative can only exist where the function exists. If the function doesn't exist, we don't even need that critical number. It's not truly a critical number, okay? So a way to think about that, as we move forward, and we're going to eventually add a second derivative is going to be important to our discussions, and we'll add a second derivative test later. We're not there yet. But one thing to keep in mind, and I'll mention this again later, is at any point, as we work down from first derivative, or from function to first derivative to second derivative, and maybe potentially even at some point third derivative, as you work on down, if there's ever a place where a function becomes undefined, then automatically all the functions below that are undefined there, right? All the successive derivatives are undefined, and those would never constitute like critical numbers, okay? Okay, so we only get 2 critical numbers. If we want to make our table now, remember what our table looks like. We've got the x-axis running across the top, and we've got a row for our x values. We've got a row for the values of the function, and now we're going to add another row to this that we didn't have previously, right? When we looked for absolute extrema on an interval, really all we had to do was just find the critical numbers and compare those values to the endpoints to see what's the absolute max and the absolute min, okay? But when we're applying the first derivative test, where we're looking for all relative extrema, we want to add another row to our table for our first derivative. Okay, so first of all, what's our domain, did we say? All reals except 0. So at 0, the function is undefined, right? Okay, so we don't have to consider that one. We had critical numbers at plus or minus the square root of 2. So we'll just add those in, square root of 2 and negative square root of 2. Those are places where the first derivative was equal to 0, okay? So what does that tell us immediately? If the first derivative is equal to 0 there, what's that tell you about what's happening with the function? Well, not necessarily, but but you know, what is going on with the topology of the function if it has a zero derivative? There's no slope, which means, well, actually there's zero slope, which means horizontal tangent line, right? So we know right away that we're going to get a horizontal tangent line, so let's draw it in, okay? How do we know what's going on with the rest of the function? We want to find all the intervals where the function is increasing and decreasing, and as a byproduct, we'll get the relative extrema. Okay, now think logically about this. What are the only places where a function could transition from being increasing to decreasing or vice versa? Right, you have to think about that. You're either going from a positive first derivative, increasing function, to a decreasing first derivative with a zero tangent line, right? So the sign of the derivative is going from positive to negative through zero, because that's all zero is the boundary between positive and negatives. Or if it's a sharp corner, then it's going from positive to negative at a place where the derivative is undefined. But it can only happen where we're at a critical number or a place where the function is undefined, if we have like a gap in the function, right? Think what that could look like. If I have a gap in the function, my function could be doing something like this. Actually, let me do that. Right? Then the place where the function's undefined, thank you. The place where the function's undefined could also be a place where we're changing from positive to negative slopes. Agree? It's not really a critical number, it's just a break in the function though. It kind of splits the function up into, you know, the intervals that surround that discontinuity. Okay? Questions on that? Does that make sense? Okay, so what do we got here? Hannah and so then come up with a strategy for me. These are the boundaries which are going to potentially be places where the behavior of the function is transitioning. How can I quickly check to see if it is? That's it. We're going to pick test values, test points. Okay? So we just want to pick some random numbers, some test values that are going to be around my critical numbers and my discontinuities, places where the function is undefined. So pick one. What's a convenient number between 0 and radical 2? Well, or even more convenient, probably 1. Let's just pick 1. So at 1, now we could work in a couple different places. I could use f, right? And I could see, is the value of the function bigger here than it, you know, I could do that, but it's not as convenient. As a general rule, we always want to work as far down the table as possible. So in this case, that means we want to work on the first derivative row instead of the function row of our table. What is the sign? And here's the thing, I don't need to know the value, I just need to know the sign of the first derivative at this test value. Okay, and I'm going to put a dashed line here because we know that's splitting the function around this discontinuity. If I go up to my f prime, it's nice to have this in factored form, because when I want to test the sign, it's really easy to do. If I want to know, for example, what is f prime of 1, I get a positive. On the top, I get a positive times, if I plug 1 in, what do I get for that factor? Positive times negative divided by positive. Well, what's the overall sign? I'm going to get negative on the top and positive on the bottom, so I get negative. You get the idea, right? So all I care about there is that the first derivative is negative, okay? What's a test point above square root of 2? 2 would be fine. So if I try this at 2, same thing. If we try, well, I wish I had a little more room on this board. So if we try f prime of 2, what am I going to get on the top? I'm going to get, would you agree, I get positive times positive times positive over positive? So the overall sign is just positive? Well, one thing I can say then is that one interval where this function is guaranteed to be increasing is all values of x greater than radical 2. How do I know it's not gonna transition and become negative somewhere else? How can I be so sure? No more critical numbers, right? And the only turning points of the function can be, all extrema are found at critical numbers. Not every critical number is guaranteed to be an extremum, but I can never have another extremum that I haven't already identified as a critical number, happening at a critical number. So I'm guaranteed that this thing is going to be boring from here on out. It's always going to be increasing to the right. Okay, so that's an increasing interval, and that's how I interpret that plus sign, right? The one other thing I could add here that makes this even a little bit clearer is I could do that, right? What's that tell me? That the domain of the function is undefined at 0, but then there is no other restriction. It goes forever, right? For all values greater than 0, and I could put a negative infinity and an open endpoint sign right there, okay? So that tells me something important. That plus sign gives me some key information, right? Let's continue on. We need some other test points. So what's a convenient test point between 0 and negative radical 2? Negative 1. Okay, now we can just probably do this one in our head here. F prime of negative 1. That's going to give me positive times negative over negative. So that's positive, isn't it? I get negative on the top and positive on the bottom. Agree? Okay, so that's going to be a plus sign. And then I could pick something like negative 2, which is going to give me positive times positive times positive, right?
You want that in the F prime? You put it in like that.
Oh, where did I put it? Oh, I did. Whoops, I did. You're right. Yeah, that's bad. It's got to go there. So this one's actually going to be negative, isn't it? I get positive on the top and negative on the bottom. And so look, now I know that the function is decreasing on the interval where x is less than negative 2. What are the other intervals? So let's write these down. I could say that f is increasing on what intervals? Okay, good. So I've got the interval negative radical 2 to 0, or right? We good? So f is decreasing on the interval from good or got it. Okay, good. Now here's the other part that's really cool. So that tells us, by the first derivative test, that tells us what's going on at these critical numbers. Now think what this has to look like. If I'm going from an interval of decreasing slope to an interval of increasing slope, and I have a horizontal tangent, what does that have to look like? Yeah, that's gonna, well, hold it. If I'm going from decreasing to increasing, I'm going from decreasing to increasing, so it's got to look like that, doesn't it? And I know that because the function is, or the derivative is defined and is equal to 0, I get a horizontal tangent. So it even tells me that it's going to be a smooth minimum, a rounded minimum. So I know what that part of the function, that's what the topology looks like. It's a smooth minimum. What's happening here? I'm going from an area of decreasing to increasing again, so that's another smooth minimum. Ready to get that? Okay? That tells me a lot about my function, doesn't it? Right? And if I just add some key anchor points, that's enough for me to graph this thing, to sketch it, right? And that's really all we want to be able to do is sketch it. So let's add just a couple other little helpful anchoring points on the function. What if I plug in this negative the square root of 2 into my function? Well, I could evaluate that. Negative the square root of 2 to the fourth power is just squared, right? So that's gonna give me negative the square root of 2 squared is 2, squared is 4. So I'm getting 8 on the top over 2 on the bottom, which is 4. Everybody agree? So we get the point, and that looks like an ordered pair, right? If I plug in positive the square root of 2, I'm getting the same thing, all right? Right? So I'm getting the point square root of 2, 4. Okay? Let's graph this guy. I think this is really cool stuff. So this table gives us enough information to draw a very useful sketch of the graph. How does this correlate to our graph? Well, here's the y-axis, right? That's where x equals 0. So look how these things line up. There's the x-axis. We've got the 2 points, negative radical 2, positive 4. So 1, 2, 3, 4, and then negative radical 2 is right about there, I guess. So we get that point, and we get that point, and those are both minima, right? And we know that this function is going to be decreasing for all values to the left, right? So an ant's walking downhill and it's increasing for all values to the right. So you tell me, what's this thing doing? Yeah, good. And we know that we get this place here where the function's undefined. And you guys can even tell me what's going on there. If I try to evaluate this function at 0, what do I get? Number over 0. Is that a whole or an asymptote? That's an asymptote, right? So we could even write in here vertical asymptote. So we know what's going on at 0. I'm getting this horizontal asymptote, and we know what this thing looks like, right? It's just looking like that. There's the function, right? Everybody get it? Okay, so could we have done anything else here that would have helped us? One other thing we could maybe do, right? We could cut our work down a little bit. Okay, we could have applied our test for symmetry also, right? Does this have even or odd symmetry or neither? It's even. Yeah, it is even. Okay, and we can see that pretty easily. If we try to do f of negative x, what am I going to get back? I'm going to get back negative x to the, negative x quantity to the fourth. It's just x to the fourth, isn't it? Plus 4 over negative x quantity squared is just x squared. So negative f of x equals f of x, so it's got even symmetry. So that tells us then, if we go back to our table, really if we took advantage of that, we could have cut our workload in half, couldn't we? We could have just done everything to the right of 0 and then just done a mirror image of that on the left side. We could have reflected it, because that's what even symmetry is. It's reflecting symmetry over the y-axis, right? So it all kind of comes together, doesn't it? Right? Okay. The other thing we could have added to our table, and probably unnecessary, but I want you to see this. The other thing we could have added is a limit. Right? We could have said, okay, what's the limit of our function as x approaches infinity? As x approaches infinity, if we go back to earlier in the year, right, if we just look at the ratio of the leading terms, aren't I just getting positive infinity here? Right? The limit of x to the fourth over x squared is just x squared. Infinity squared is infinity, right? So the limit as x approaches infinity is positive infinity. What's the limit of the function as x approaches negative infinity? Positive infinity, right? Everybody see that? Because I'm getting x squared. Well, the limit of x squared as x approaches negative infinity is negative infinity squared, which is positive infinity, right? And so we can also see then that the tails of the function are what we thought they were going to be if we do the limit. How is that helpful to us? Well, it wasn't so necessary here, but what if our limit had been something that's constant, so we'd gotten a horizontal asymptote? then the asymptote would have showed up in our sketch. Right? So you see how this brings everything we've talked about comes together on this table. It's pretty cool. Okay, let's do another one. Let's just practice these a little bit. So what about this guy? What are we gonna do? Oops. We can already start to draw our table a little bit, right? Because what's it tell us about the domain? 0 to 2 pi. Okay, so we can already start. Okay, and we know that we can go 0 on the left, 2 pi on the right, and it's an open interval. Okay? Any place where our function's undefined? No, we're good. Sine functions don't have any asymptotes, right? So we're good. So then we just need a derivative. So what's f prime? And that, remember, sine squared is like sine x quantity squared. Okay? Cosine x, right, by chain rule. Okay? All right, is our first derivative undefined anywhere? No. So we're just looking for zeros of the first derivative, right? So we've got to just solve the equation then. F prime equals 0 when 2 sine x cosine x plus cosine x equals 0. Okay, it's always good to get a little practice solving trig equations because they're hard and you don't do very many of them. And you guys are scared about trig probably a little bit like everybody is in high school. Okay, so what do we do?
Move that cosine.
Good, we want to factor it. So we'll factor out a cosine x.
Yeah.
Good job.
Is that what you were saying?
Yes,
Okay.
that is what I was saying.
Love to see it.
Okay, all right?
Then we can use the
Zero product property. You see how useful that is? If we can factor this thing by the zero product property, the product of the factors is 0 when each factor is 0. So we've got cosine x equals 0 where on our interval?
Oh,
What?
Think unit circle.
Earth.
I should have the unit.
So cosine is the x coordinate, right?
Yeah.
So it's going to be there. So we're going to get that spot and that spot, right? So between 0 and 2 pi, that's going to be at
Pi
But-
over 2.
pi over 2 and
Negative. Or
Okay, but-
Pi over 2.
3 pi over 2, right? On our interval. Agreed?
Yeah.
Okay, so critical numbers there. Okay, and I can add those critical numbers. I'm going to hold off on that just to maybe because I want to be able to space them appropriately, right? So there's some critical numbers. What about the other one? So the other one we get 2 sine x plus 1 equals 0 when, isn't that just going to be where sine x equals negative 1/2? Everybody agree? This one?
Yeah.
If I said it equal to 0? Okay, so where's that going to be? Where is sine x equal to negative 1/2? So that's going to be at that point and that point, right? Where the sine, which is the y-coordinate, is negative 1/2. So I'm going to have the point with y-coordinate negative 1/2 and the point with y-coordinate negative 1/2. X-coordinates would just be would be plus square root of 3 over 2 and negative square root of 3 over 2, right? Where are those? You just got to know that unit circle. So this one is going to be I probably should put it up there a little bit more. It's going to be a big X value, square root of 3 over 2, and a small negative Y value. What is that one? In quadrant 1, it would be right there, right? So what's that angle? Pi over 6, okay? So then it's gonna be almost all the way around. It's 2 pi minus pi over 6. 11/6 pi. Okay, so one place we're gonna get that. Or, right over there would be 7/6 pi, right? I'm gonna do pi halves plus an additional pi 6. So if I add all those critical numbers in, I've got, let's see, I've got pi halves. I've got 3/2 pi. And I've got 11/6 pi, which is gonna be squeezed in here, right? Yeah, I gotta move these a little bit. That's gonna be too hard to. So these are gonna be a little bit out of scale. That's all right.
Also, sure, it's going to be. It happened if I can find my system. Also, if you get like one of the quarterbacks, it's got like game plans.
11/6 pi and 7/6 pi. Okay, everybody agree those are all places where the derivative is 0?
Yeah.
I got lost. a
Okay.
while ago.
Okay, well, let's get you unlost.
Okay.
Right, what did we do? We found critical numbers where the first derivative is equal to 0. That happens where cosine x is 0, which is at those two places,
Okay.
and where 2 sine x plus 1 is 0, which is where sine x equals negative 1/2,
Okay.
which is at those two places on the unit circle, on our domain, right?
Okay.
Okay? And I know that you gotta think about the trig stuff a little bit, but you can all get there, right? So now we have to just pick some test points surrounding those, and that's gonna tell us everything we need to know. Increasing, decreasing intervals, and also if and when they're a relative extrema, okay? So let's pick some convenient test points. And in this case, they may not be very convenient, okay? So if I were to pick, for example, what's a value between pi halves and 7/6 pi, there is no convenient value for us on the unit circle, right? So that would be something like, we'll just do like, we can even just kind of fudge this and say something like 0.501 pi, just something, we'll just pick a value in between there. I don't even have to write it down. Let's see if we can come up with what the sign of the function is going to be there. If I'm picking a value on the unit circle that's like right there, right? Isn't that where we're picking? Oh, hang on.
You can just use.
Yeah, can't you just use?
Oh, yeah, we could. What am I saying? Yeah, we can just use pi. Yeah. So there is a very convenient one. I don't know what I was thinking. There's a very
I don't know what you were
convenient one.
thinking.
Yeah, we'll just pick pi. We'll just pick pi.
Yeah.
So what's the sign of pi?
1,
Sign of pi is 0, isn't it?
0.
Right?
Yeah.
So I'm getting 0 squared plus 0. So I get sorry. I don't want that. I want first derivative. The sine of 0 is 0. So the first term goes away.
Yeah.
Agreed? Plus the cosine of 0 is, cosine of pi. No?
It's negative.
Negative 1, right?
Yep.
Okay, so I'm getting a negative result from that one, right? Okay, what about, we'll pick, in here we could pick, what's a value between there and there? So I could pick something like 3/4 pi. 5/4 pi.
Yeah.
Okay, everybody agree? 5/4 is between, that's going to be the one right there that's between those two, right? At 5/4 pi, sine squared is going to be positive regardless because it's squared.
Aren't we doing the derivative?
Oh, sorry, we already did it again. Sine is going to be, look right there, both sine and cosine are negative, aren't they?
Yeah.
Right, everybody with me? You guys got to keep me on track here. It was 2:30 arrival last night. I'm gonna always go to that line that looks like every time instead of the F prime line. So we're gonna get negative and negative for sine and cosine, right?
Yes.
So this is gonna give me 2 times negative square root of 2 over 2,
Uh-huh.
positive square root of 2 over, or negative square root of 2 over 2, doesn't matter, it's positive, right?
Yeah.
But square root of 2 over 2 times square root of 2 over 2 is just 1/2. So I'm getting 2 times 1/2 is 1, right?
Yes.
Plus the cosine of 5/4 pi is gonna be negative, but it's less than 1.
Yep.
Everybody with me? And wouldn't it even be easier, I guess, if we used, maybe this would be a little bit easier if it's in factored form. Either way, though, we can reason that certainly the overall sign is gonna be positive, right? What's a value, convenient value between 3/2 pi and 11/16 pi? Well, we would just do like 7/4 pi, would be probably an easy one. So there, we're getting positive cosine and negative sine.
Yeah.
Everybody agree? So I'm getting positive times negative, but the values are the same, right? They're square root of 2 over 2 and square root of 2 over 2. It just changes the sign of that term. It's going to be a -1 plus positive something less than 1, right? So it's negative. Below pi halves, we could just pick pi fourths. Pi fourths, we're going to get positive and positive, right? So positive and positive and positive, I get positive. Good? The only place we have left to pick, and this is an inconvenient one, is right here. Agreed?
Yeah.
Okay, now here's a trick. There's no convenient value between 11/6 pi and 2 pi, but this edge of the interval of our domain is arbitrary, right? So why don't we go ahead and just use 2 pi, right? Because there's no reason that we didn't pick it other than the fact that we were told to use this domain. Now, you hang with me, you'll get this. So if I plug 2 pi in, that's an easy one, that's right there, isn't it? So we know that the sign is 0, so I'm gonna get 0 plus 1, it's positive, isn't it? Right? Well, if the value of the function at 2 pi is positive, then really we could have just as well done a limit, right, as we approach from the left.
Uh-huh.
Everybody with me on that? You gotta really focus on that one, right? So this is still an okay one to do, as long as we just think of it as being a limit, right? It's still giving us a value of the derivative as we approach 2 pi, and it's positive. Isn't that cool? That's a pretty cool way to do it. I mean, isn't that just like everything that we've done comes together in this table? And I have to tell you, this table is kind of my little baby. This is one that, the way they do it in all the textbooks is different, but I'm very, very proud of my approach to the table. So get this one down. I think this is my one and only positive contribution to teaching the high school calculus, and my big deal is the table. You'll find the table is helpful to you. So now, if we wanted to, look, we got all these intervals, right? We know the function is increasing on this interval, it's increasing on this interval, and it's increasing on this interval, right? It's decreasing on this interval and this interval, and you tell me, what kinds of extrema do we have? We have a 0 first derivative, so we get a horizontal tangent line, horizontal tangent line, horizontal tangent line, horizontal tangent line. We're going increasing to decreasing. Is that a maximum or minimum? Maximum. It's a smooth maximum. There's a topological feature of our function. We're going from decreasing to increasing, so walking downhill to uphill. Increasing to decreasing, decreasing to increasing, and there you have it, right? So we can see right now we've got 2 relative maxima and 2 relative minima, right? And we know the intervals on which this function is increasing and decreasing, so that's enough. Are we out here at 25?
Yeah.
So that's enough for us to sketch this thing, right? Really, all we'd want to do maybe is just include some values of the function to anchor this thing, right, at our critical numbers. So like at 0, what would we get? We'd get 0, wouldn't we? Right? So even though that's not a point we're including, that's the point we're approaching, right, at the endpoints. At 2 pi, we'd get 0, right? That's the value we're approaching. At pi halves, what would we get? At pi halves, we're getting 1 plus 1 is 1. I'm sorry, it's 2. right? Right? Everybody agree? At 3/2 pi, that would be down here, we're getting -1 squared plus -1 is 0. Everybody agree?
Uh-huh.
These would be a little tougher, right? Those ones wouldn't be as fun to do. We're at 7/6 pi, so that's right there. We get -1/2 as our sign value, right? So we're gonna get +1/4 plus -1/2 is -1/4. There's a point. At 11/6 pi, same thing, right? The sign is still -1/2. So if I plug that in, I'm getting -1/4, whoops. And now if I do a quick sketch, that's all I need. We've got, what are my points? 0, 0, square root of 2 over 2, 2. You know, I mean, you get the idea. We can finish this one up tomorrow, but then we'll let you work on this stuff a little bit.